In this video, I'm going to talk you through the AQA GCSE Combined Science Trilogy Physics Paper 1. This is the higher tier paper. I hope you enjoy. So we'll start with question 1. It says figure 1 shows two models of the atom. We've got plum pudding model here and we've got the nuclear model there. And in the first part of the question, we're asked to write the labels onto figure 1. And we're allowed to choose from these answers here. It's worth 4 marks, so we get a mark for each of the ones we label correctly. So if we start with the plum pudding model, is this one here, we can see we've got a negative charge, which we know should be the electron because of the negative charges, and they're dotted around inside a positive gas. Which if we look for this one here, we're going to try and find out what the positive gas is, and we'll say that that's the atom, because this is the early model of the atom. So you can see there we've got the first 2 marks by writing electron, this place, and we've also got the atom here. If we look at the nuclear model now, we've got 2 labels to add onto this one. And the nuclear model, if you remember, consists of electrons, and then what we've changed in the model is that we've now got a nucleus in the centre, and we've got electrons orbiting the outside on orbitals or in electron orbits. So we can label this as the nucleus and this as the orbits. So now they're labelled for you, so you can see that I've labelled the nucleus and the orbits here. You can mark that question, and we'll move on to question 1.2. Which is explain why the total positive charge in every atom of an element is always the same. So the first marking point is saying that every atom of an element contains the same number of protons. So you should know that all atoms of carbon, for example, contain 6 protons, because that's what makes it carbon. Oxygen contain 8, etc. The next marking point is saying that the protons provide the atom with a positive charge, and that is why all atoms of any element have the same positive charge. You get the positive charge from a proton, and which is this marking point here, and each atom of any element will have the same number of protons, therefore they have the same positive charge. Question 1.3 says the results from the alpha particles chemistry experiment led to the nuclear model. Alpha particles were fired at a thin film of gold at a speed of 7% the speed of light. In order to determine the speed of the alpha particles, given that the speed of light is 300 million meters per second. So this question is just asking you to find 7% of 300 million meters per second. So to calculate this equation, you're going to use the equation that speed is equal to 7 over 100 to turn 7 into a percentage, and you multiply that by 300 million. So 7 over 100 is 0.07, multiplied by 300 million, and that will give you the answer. So that gives you an answer of 21 million meters per second, or 2.1 times 10 to the 7 meters per second. Don't be afraid to leave your answer in standard form. In terms of the marks for this question, it's a mark for showing you're working here, and it's a mark for getting the correct answer. If you do get the correct answer without any working, you do get 2 marks. So for the next part of the question, it says figure 2 shows 2 atoms represented as solid spheres. You've got magnesium here and hydrogen. It says the hydrogen atom has a radius of 2.5 times 10 to the negative 11 meters. Determine the radius of the magnesium atom. Use measurements from figure 2. So here you need to measure the size of these atoms using a ruler. And when I did my measurements, I came out with the following, where I got 7.6 centimeters for my magnesium, and I got 1.3 centimeters for my hydrogen. And what I then need to do is I need to work out a ratio of these 2 values, and then I will multiply my hydrogen radius by the product of that ratio. So I'm going to do 7.6 divided by 1.3 to get myself an answer, and then I'm going to multiply that by 2.5. So my calculation for my question and my measurements is shown here. I'm doing the 7.6 over the 1.3. I'm going to multiply that by 2.5 times 10 to the negative 11. You will get a mark by writing out your measurements here, as long as they're in range. And if you divide those by each other, they should give you a value of around about 6. Mine comes out as 5.8. When I multiply that by 2.5 times 10 to the negative 11, that will give me the correct answer. the correct answer should be about 1.5 times 10 to the negative 10. You can see the correct answer there as 1.5 times 10 to the minus 10. I thought it would be useful just to show you the mark scheme for this question. So you can see you get 1 mark for doing the 6 multiplied by 2.5 times 10 to the negative 11. You'll notice that you basically get the mark for getting a 6 in there. If you had a value between 5.7 and 6.3, that's acceptable. And you correctly substitute it into there again, that's correct, acceptable. And then your final answer, you get 1.5 times 10 to the minus 10. You're allowed an answer in the range of 1.4 to 1.6. And that's how you get the marks for this question. Question 2. A student wanted to determine the density of the irregular shaped object shown in figure 3. This is a nice chess piece here. And it wants you to plan an experiment that would allow the student to determine the density of the object. And it's going to give you 6 marks for this question. So this is an extended writing question. It's really important that we write with capital letters and full stops to make sure we presented our work in the best way. And we need to try and include as much detail as possible here. So how you'll be assessed is based on these 3 level descriptors here. So you can see level 3, the method would lead to the production of a valid outcome. All key steps are identified and logically sequenced, and that'll get you a mark of a 5 or a 6. To get level 2 answer, the method will not necessarily lead to a valid outcome. Most steps are identified, but the method is not fully logically sequenced, and that will get you a mark of 3 or 4. For level 1 answer, the method will not lead to a valid outcome. Some relevant steps are identified, but links are not made clear. So things the example are expecting you to include is shown here under the indicative content. So the key thing for me is that how you work out density using this equation here, density is mass over volume. And if you remember that that's how you work out density, you need to recall that, you need to learn that. You can then try and break down that formula and use that to structure your answer. So we know that we need to find density, we need to find mass and then volume. How do you find mass? Well, you're going to use the top pound balance to measure the mass. To find the volume, the method we use at our school was to fill a displacement or eureka can with water. You put the water level up to the spout, you place the object in the water, and you collect the displaced water once the object's been added to it, and you collect that in a measuring cylinder, and that allows you to measure the volume. Once you've got the mass and the volume, you use density equation, mass over volume, to calculate the density. So you might want to use this indicative content to improve your answer. And once that's improved, you need to look at this side, the level descriptors, to see if your answer would allow you to get there. But if you said how are you going to measure mass, you said how are you going to measure volume, and you said you're going to use the density equation to do mass over volume, you'd have got 6 marks for this question. Question 2.2 says another student did a similar experiment. He determined the density of 5 common plastic materials, and he shows the results in this table, which is here. And then it says that figure 4 shows the results plotted in a bar chart. You can see we've got acrylic and nylon. I would like you to then write the correct scales on the y-axis and draw the bars for polyester, polystyrene and PVC. So the first job is to try and work out the scales. To do that, I'm going to need to remember what the values of acrylic and nylon are. So I'm just going to highlight those in the table. So you've got acrylic here and nylon there. Okay, so you can see that nylon's 1,000, and that the 1,000 line is this line here. So we know this line here is going to be 1,000, so we can add that onto our diagram. So if that line's 1,000, then we've got 2 other thick lines, which mean that 10 squares count towards them here, and then 1 here. So if this one's 1,000, we know that this one must be 500, assuming we're starting at 0. So we have 500, 1,000, and then 1,500. So these are the only labels that we need, because these are the thick squares. So having 500, 1,000, and 1,500 labelled on the thicker lines that are every 10 small squares, we get the mark here. Now just to double check that's correct, we said this is 1,000, and we know that acrylic should be 1,200. So if every 10 squares is 500, that means that every 1 square is 500 divided by 10, which gives us each small square is worth 50. So up from 1,000, we should have 4 small squares before we reach acrylic. So you can see 1, 2, 3, 4. And so again, we know we got our scale correct. So the marks for scale, we get 2 marks for getting 3 correct labels on here. So these 3 labels we get as 2 marks because that's the first marking point. First question is getting the correct scale, and that's worth 2 marks. The second marking points are for getting these plotted correctly. So what we need to do now is we need to go through the process of trying to plot those correctly. So the first one we need to do is polyester at 1,380. So we said that this line's 1,000. Okay, and we also said that each small square is worth 50. So starting on this line at 1,000, 1,050, 1,100, 1,150, 1,200, 1,250. So that's the 5th square, 1,250, which is slightly thicker than the rest. And then we go up from there to go 1,300, 1,350, and then the plot for polyester should be in the middle between these two. So 1,350, and then we've got 1,400 above it. And that's where you should place the line for polyester. So in terms of where that one should be, that should fall, if you count backwards from 1,500, 1,500, 1,450, 1,400, so that's 2 squares down. So it should be between 2 squares below 1,500 and 3 squares below 1,500, because that would be between 1,350 and 1,400. In a moment I'm going to put a image of a graph paper on so you'll be able to see that slightly better. The polystyrene one is at 1,040, so again you start at 1,000. Above there is 50, so the 1,040 would come in between those 2 squares, between the 1,000 and the 1,050 square, so just above the 1,000. And the final one is PVC, which is at 1,100, so that will be the second square above 1,000, because we go 1,000, 150, 1,100. So as promised, I've uploaded my my graph, and you can see here the points that you need to do. So with 1,380, you can see that we've gone for 1,250, here 1,300, 1,350, and then we're in the middle of that one before I reach the 1,400 mark. And again, the same with the 1,040 for polystyrene, I've gone between 1,000 and the 1,050 mark. Okay, and then PVC is a nice one because it goes at 1,100, and so it's 1,000 there, 1,050, 1,100. I've also added the extra labels on to my graph paper so you can see those as well, but that graph there will get you the 4 marks for this question. Remember, it's 2 marks for getting 3 of these labels on the graph, and it's 2 marks for getting all 3 of these correct. If you got 2 of them correct, you get 1 mark. If you got only 1 of them correct, you get no marks. The last part of question 2 asks you to determine the uncertainty in the student's results is collected here. So you can see the density, and you've got a range 960, 1,120 and 1,040. Now you should know that the range, or the uncertainty, is given by half multiplied by the range of your values. So you can see I include that equation here now, and the uncertainty is half times range. What's the range? Well, the range is your highest value, so 1,120, minus your smallest value, which is 960. So you see we put on there the working out, so we've done a half multiplied by our range, which is 1,120 minus 960, so that's a half times 160, and that will give us an answer of 80. So you get 2 marks getting the correct answer, 80, which is here, but you'd also get 1 mark for getting 160, or you get a mark for putting this calculation here if you worked out this one wrong. So by doing a half times 1,120 minus 960 is 1 mark. Working that out to be 80 gets you a second. So moving on to question 3, you're given the figure 5 shows a diver. The diver is using a canister of compressed air so you can breathe underwater. Which 2 sentences describe the movement of the air particles in the canister? And you've been asked to tick 2 boxes. So you run through the possible answers for this question, and you can see that they vibrate around a fixed position. Well, the canister is going to be compressed air, so that's a gas, so it won't vibrate around a fixed position because that's a solid particle. They move in random directions. Well, gases do that, so that's probably going to be one of the correct answers, but we'll read the rest. The motion of all the particles is predictable. Well, no, it's not, because they're gas particles and they move in random directions, so that's incorrect. They move at a range of different speeds. Well, that's true of gas particles. And they move in circular paths is incorrect. So two correct answers are they move at a range of different speeds and they move in random directions. So you tick those two boxes as shown there, and that will be the correct answer for this question. You get 2 marks, 1 for each of the correct boxes ticked. Question 3.2 says the temperature of the air inside the canister increases. What happens to the movement of the air particles? Here what you need to get across is that as the temperature of the air inside the canister increases, the particles are going to have more energy, more kinetic energy, so they're going to move around faster. So their movement, their speed increases. So I put here that the mean speed of the particles increases, and this is because that they're moving around at a faster rate on average. Not all the particles, not every single particle in there would have a faster speed, but the majority of the particles would, and therefore the mean would increase. You could also get a mark for saying that the kinetic energy of the particles increases as well for this question. So question 3.3 says it could be dangerous if the temperature of the air inside the canister increased by a large amount. Explain why. Well, the marks here are for saying, well, if the temperature increases, what happens to the particles? Well, the pressure of the particles is going to increase. If the pressure inside the canister increases, it could lead for the canister or container to explode or burst. So you get 1 mark for saying that the pressure increases, and a second mark for saying that could lead to an explosion. So you can see I put the correct answer in now. As the temperature increases, pressure increases, 1 mark. The particles exert greater force on the canister, which could lead to an explosion. Now, it's only the word explosion here, or the canister being damaged in some way, that will get you the second mark. So now it says that a canister of air was tested to find out how the pressure changed when it was used by a diver. Air was allowed to escape from the canister. The pressure of the air in the canister was recorded every 5 minutes for 80 minutes. And it says figure 6 shows the results. Estimate the atmospheric pressure using figure 6. So the atmospheric pressure will be achieved when the pressure of the canister is equal to the pressure of the air surrounding it. So what we're seeing is the pressure decrease inside the canister until it levels out, and where it levels out, that's the atmospheric pressure. So we need to read this value off the graph. Okay, and we can see that each 5 small squares gives you 0.5. So we can see that line there where it's leveling out is at 1 small square. So that will be 0.1 megapascals. I've placed the correct answer in now. You can see 0.1 megapascals, and that's because that's where the line levels out. 3.5 says divers can safely stay underwater until the pressure of the air in the canister has reduced to 25% of its original value. It asks you to determine the maximum time the diver can safely stay underwater. So to be able to do this question, what we really need to do is we need to be able to see the graph. So I'm going to bring the graph into this page here, and then we'll work it out from there. So now I've dropped the graph in, and you can see graph figure 6 is down here, and we just need to try and figure out what we need to do in the question. So if we look at the question, it says divers can safely stay underwater until the pressure of the air in the canister has reduced to 25% of its original value. Determine the maximum time the diver can safely stay underwater. So we need to find 25% of the original value, and then we use that to read off to find our time. So you can see that value on the graph is somewhere between 2.2 and 2.3. So the value that we read from the graph there, if it's halfway between them, it would be 2.25 megapascals. And we need to work out 25% of 2.25 megapascals. So to do that, to find 25% of it, 25% of it you could do by completing 0.25 multiplied by the 2.25. And that will give us an answer. And that gives us an answer of 0.56 megapascals. So what we then do is we go to the 0.56 line. I'm going to have to read across 0.56. So you can see that there's 0.56 going to be halfway between there. We go across that one and come down. And you can see, I know I've used a relatively thick pen there, but you can see the answer is going to be between 20.6 and 26 and 28. Use a finer tip pencil, I would have got an answer there to be that the answer would have come out to be 27. So our answer should be, for that question, 27 minutes. And we've got that from reading off the graph as I've shown here. So 5.6 would be, 0.56 would be in the middle of this line. It would strike there and then come down in the middle of that one. And that's in between 26 and 28. So that's where we get the 27 from. The final question says, what happens to the volume of air when it is released from the canister? And the answer to that question is that the volume increases. And that brings us to the end of that question. So add up all your marks and give yourself a mark out of 10. So question 4 says the Chernobyl disaster was a nuclear accident that happened in 1986. The radioactive isotopes were released into the environment, and the radioactive isotopes emitted were alpha, beta, and gamma radiation. 4.1 says what is an alpha particle? So an alpha particle, if you remember, is a helium nucleus, and that would be 2 charged particles and 2 neutral particles would be the best description of that. Because remember that you've got helium, and that's 4 and 2, so you've got 2 protons which are charged and 2 neutrons which are neutral. So that's the correct answer there, is the first box. 4.2 says which statement about beta radiation is true? Tick one box. So is it a fast moving type of radiation? Well, beta's not the fastest because gamma is actually the fastest. It's a type of radiation with a negative charge. So beta, remember, is an electron, so it does have a negative charge. So that's the correct one. Is a type of radiation with the greatest mass? Well, no, because that's alpha particle. And it's a type of radiation with the greatest range in air? No, that's the gamma radiation. So we know by discounting the other ones that we've definitely got the right mark, and the correct one is it's the type of radiation with a negative charge. Moving on to question 4.3, it says which statement about gamma radiation is true? So remember that gamma radiation is a high energy electromagnetic wave. So it's a low frequency EM wave, that's incorrect. It's a high frequency one. It causes the charge of the nucleus to change? Well, not necessarily. It causes the mass of the nucleus to change? Again, no. And it has a very long range in air. So it does have a very long range in air. And when a gamma ray is emitted, it does not cause any change of the nucleus. Okay, it can sometimes cause charges to change if it ionizes something, but usually that doesn't happen. So the best descriptor is that it's got a very long range in air. So the next question we're going to move on to shows a table to begin with, which you can see here. We've got isotopes and half-life. And it says a soil sample was taken from the area around Chernobyl in 1986. The soil sample was contaminated with equal amounts of cesium-137, which has a half-life of 30 years, and iodine-131, which has a half-life of 8 days. Explain how the risk linked to each isotope has changed since 1986 and 2018. Both isotopes emit the same type of radiation. It's worth 4 marks. So I imagine you're going to get 2 marks for talking about cesium and 2 marks for talking about iodine. So what we need to talk about now is what will happen to the risk associated with each of them. So the risk will decrease for the longer period of time that each of these are left, because as the time you leave them for, basically they go through the half-life, so they emit less radiation. So you take cesium to begin with. Cesium has a half-life of 30 years, which means that actually by 2018 it hasn't really gone through very many half-lives. So therefore, the risk associated with cesium hasn't decreased by much because it's got a long half-life, and that will get you 2 marks. So with that, you get a mark for saying that cesium's got a long half-life, and that means that the risk associated with cesium hasn't decreased by much because it's, the half-life's so long that the activity hasn't dropped, which hasn't gone through very many half-lives. Now, the second set of marks is for saying that the risk associated with iodine has decreased by a large amount, and that is due to the small half-life of iodine. Okay, so iodine has a half-life of 8 days, and so you can imagine it's gone through very many half-lives in 8 days, if it's only 8 days, over the years between 1986 and 2018, and therefore the risk associated with that has decreased significantly. Next part of the question says determine the year when the activity of cesium-137 in the soil sample will be at 1/32 of its original value. So the first thing we need to find out is how many half-lives have passed in this time. So here what we want to do is we want to find out how many times you have to multiply 2 by itself in order to get 32. So if you look at this side of the screen now, you can see we start off 1 half-life would be when it went down by a half. A second half-life would be decreased by a quarter. A third half-life would be when it decreased by an eighth. A fourth half-life when it would decrease to 1/16 of its original value. And finally, the fifth half-life will be when it decreased to 1/32 of its original value. So we know we've gone through 5 half-lives in order to reach 1/32 of its original value. So by getting across the answer of 5 half-lives, you get yourself the first mark for this question. Now for cesium-137, each half-life is 30 years, so we've now got 5 of those 30 years. We're going to do 5 times 30 to find the total number of years. So you can see here that would give you 150 years. That's the second mark now, is how long it would take to go through 5 half-lives to get to 1/32 of your original value. So we know it's going to take 150 years, and now we need to add 150 onto 1986 in order to find out when that would actually happen. So you can see here that now we've done 1986 plus the 150, and that gives us the year 2136, and that will get you 3 marks for the question if you get 2136. Please add up the marks for the question and give yourself a mark out of 10. Next question is question 5. It says figure 7 shows cavity wall insulation being insulated in the wall of a house. You can see the diagram here. You've got brick and a block, and you've got the cavity wall insulation going in the middle here. It says explain how the wall reduces unwanted energy transfers. So for this question, I've just added the marks given onto the question so you can see how you get the marks. So the first mark is saying the wall has 2 or 3 layers, and you are allowed the wall is thick if you have written that down, but mainly we're looking for that it's got multiple layers. Cavity wall insulation in particular, and the brick block has a low thermal conductivity, so a mark for getting across the idea that they've got low thermal conductivity. And finally, what does that mean? That means that less energy is transferred by conduction, so allowed rate of energy transfer is lower. No, any reference to convection or radiation is just ignored. So the one you need to talk about is conduction here, and basically you're saying that the rate of energy transfer due to conduction is lower because you've got low thermal conductivity in the brick and the insulation. So in this question, it tells you that 5.2, the cavity insulation was tested, the heating inside the house was switched off, and the temperature inside the house was measured every 20 minutes for 2 hours. And you can see here that because the heating is switched off, we get a lower temperature as we go down. In which to determine the temperature inside the house after 30 minutes. So after 30 minutes, we're going to have a value less than 20, 20.8, and higher than 17.4. Now 30 minutes is halfway between 20 and 40, so that's going to be half the distance between them. So what we can do is we can do 20.8 minus 17.4. So we can now see that 3.4 is the difference between them. So that's 20.8 minus 17.4 is 3.4. And if we half that, we'll find half the difference between them. And then if we either add that 17.4 or subtract it from 20.8, that will give us the value at 30. So you can see the difference between them is 1.7, half the difference between them is 1.7 degrees Celsius. And so if I subtract that from 20.8, I'll get the value for 30 minutes. So as you can see here, 20.8 minus 1.7 gives you 19.1 degrees Celsius, which is the correct answer. And the marks are for finding half the difference being 1.7, and then finding the correct answer being 19.1 degrees C. Instead of doing 20.8 minus 1.7, I could have done 17.4 plus 1.7, and it would still give me the same answer of 19.1 degrees Celsius. In question 5.3, it says figure 8 shows the gas boiler used to heat the house. And you've got, in the figure 8, you've got a hot exhaust gas here, hot water going this way, cold water coming in, and hot water going out, and you've got the fuel underneath. It describes how different energy stores are changed by the boiler. So what I've done is I've dropped the mark scheme in for here, and I'll just talk you through that so you get a mark for each of these different points that we're going to put on. So the first mark is for saying that chemical energy store of the fuel decreases, because you obviously burn the fuel and therefore the chemical energy store is decreasing. It's being transferred to other things. The thermal energy store of the water increases, the second mark, but you're allowed to have that the kinetic energy store of the water particles increases. But basically the heat energy associated with the water particles increases. And also the thermal energy store of the air also increases. So it's a mark for chemical store decreasing of the fuel, thermal energy store of the water increasing, and thermal energy store of the atmosphere increasing. And that gives you the 3 marks for this question. Question 5.4 says to heat the house, the boiler transfers 15 megajoules of energy in 10 minutes. In which to calculate the power of the boiler, write any equation that you use, and it's worth 4 marks. So I'm going to use the equation that power is work done over time, or remember that work done is the same as energy transfer. So that's the equation I want to use for this question. What I need to do then is I need to convert these units. Okay, so if we look at these ones, we've got 15 megajoules. I've also got 10 minutes. So I need to convert them into the correct units. So I need to convert 15 megajoules into joules by timesing by 1 million. I need to convert 10 minutes into seconds by timesing by 60. So out of the two conversions, you can see here I've put time is 10 times 60 to get 600 seconds, and work done is 15 times 1 million to get 15 million. And now I just need to put these into this equation, I'll be able to work out my answer. So then you can see I've put 15 million over 600, and that gives me an answer of 25,000. And 25,000 there is the correct answer. So if you get 25,000 watts, you get all 4 marks. But in terms of where the marks are allocated, you get a mark for doing 10 times 60 at 600 seconds, that's 1 mark. You get a mark for saying 15 times 1 million to get 15 million joules, that's the second mark. And then you also get a mark for saying 15 million over 600. Getting that all out to be 25,000 gets you the 4th mark. So please now mark your work and give yourself a value out of 12. Question 6 is a student builds a circuit using filament lamps. Sketch a current potential graph for a filament lamp on figure 9. So now I've uploaded a graph that you should have drawn here. So you can see this is the graph that you should have drawn. You should have had a line going through here. So there's a line going into these two sections, and the fact that it curves at either end as well. Okay, so it's 2 marks, 1 bit for the curve and 1 bit for it being in this quarter and this quarter. This question is quite a difficult one for 6.2. It shows you that figure 10 shows the circuit with 2 identical filament lamps here and here. It says compare the current, say I1, I2 and I3. And you've got to kind of use this as a mathematical expression. Okay, so the idea is that I1 is going to have the same is a total current in the circuit, and what happens when it reaches here is it splits into I2 and I3. So I2 plus I3 will give you I1. I2 and I3 will be equal to one another because they are identical bulbs and therefore the same current. So you could have any of the following two, as I've said before. So I1 is the total current in the circuit, and that splits to form I2 and I3. So I1 equals I2 plus I3 will get you 1 mark. I2 and I3 being the same would also equal 1 mark. And then really realising because it only splits here, that I2 will be half as much as I1. So I1 would equal 2 times I2, or I1 would also equal 2 times I3. So any two of those would get you the marks. I personally find that the first two are the most logical to come up with. The next question is 6.3. It says calculate the charge that flows through the cell in 1 minute. Each filament lamp has a power of 3 watts and a resistance of 12 ohms. Write any equations that you use and give your unit for your answer for charge flow. So with this question, I would always say the first thing to do with any of these is to get the unit down first. So we need the unit of charge, which is coulombs, or just a capital C. And by ensuring that we've written the units already, we get the mark for that. So we know that we've got that sorted. And now what we need to do is now try and figure out what charge is. The best thing to do here is to try and look at the things we've been given in the question. So you can see here that we've got 3 watts, so we know that's a power. We've also been given, I'm going to highlight this in red as well, 12 ohms. So I'm going to use those in the same equation, and then we've got 1 minute, which is a time. So we know power, resistance, and time. Oh, we just need equations that link those together now. So I've written the two equations that I'm going to use, which is P equals I squared times R and Q equals I times T. So the first one I can do is I can find my current using P equals I squared times R. That's my first step. And then I'm going to use Q equals I times T to find my charge. So you can see I'm going to use the equation that P equals I squared times R. And I put the numbers into the equation then to get 3 equals for power, I squared times 12 for my resistance. And that gives me 3 over 12 is equal to I squared. So if I do 3 divided by 12, I get an answer of 0.25. And if I square root that answer, I get an answer for I being 0.5. So you can see now my answer for I, following that working through,
Square root of 0.25 equals I, and 0.5 equals I. So now I'm going to take my 0.5 and add that into this equation, but I first need to change my time from 1 minute into seconds. So you can see here that I've done my time is 1 times 60 at 60 seconds, and now all I need to do is put them into this equation. So I'm going to have 0.5 times 60, and that should give me my charge. So I add these into this equation here, so you can see that Q equals I times T. So I've done Q equals 0.5 for my I, multiplied by 60, which is my time, and that gives me 30 coulombs, but that is only for one bulb, okay, because it tells you the power of each lamp is 30 watts and the resistance of 12. So what I now need to do is I need to multiply this answer by 2 to find out the amount of charge transferred on both bulbs, because I've got 2 bulbs in my circuit. So I do 30 times 2 to find the total charge stored in the circuit. So you can see here that I've done at the bottom, total charge is 2 times 30 to get me the 60 coulombs, and 60 coulombs is my final answer, and that would get me all 6 marks. To emphasise with the marks given, you get 1 mark for substituting correctly here, 1 mark for rearrangement, and 1 mark for that answer. You then get another mark for substituting into there, and you get a final mark for getting times by 60, and obviously the last mark is for your units, which is coulombs. So hopefully that explains where all the marking criteria are. So you remember 1 for substituting in to the P equals I squared times R equation, 1 for rearranging and getting an answer of 0.5, and then the final, then 1 for doing Q equals I times T and 0.5 times 60, and then the final mark for getting the 60 coulombs. So please check through all your work and make sure you're happy with how that's marked. So now on to the final question of the paper, question 6.4, and it says a student builds a different circuit shown in figure 11, where you've got an ammeter in series with a resistor, which is in series with a light dependent resistor on LDR. You've got the voltmeter across there to measure the potential difference, and then you've got the cell that's providing power for the circuit. In which you explain how the readings of both meters change when the environmental conditions change. This question is worth 6 marks, so it's important that we make the good use of proper English, and including capital letters and full stops. So in this question you're going to be assessing the following way. To get a level 3 answer, which gets you 5 or 6 marks, you need relevant points, reasons / cause are identified, given in detail and logically linked to form a clear account. If you get a 3 or 4 marks, that's a level 2 response. And the reason for that is that you've got relevant points, such as the reasons and cause identified, and their attempts to link logically. The resulting count is not fully clear all the time. Finally, if you get 1 or 2 marks, the reason for that is that you've got points that are identified and stated simply, but their relevance is not clear, and there's no attempt at logical thinking. So the idea is you've got to explain yourself logically and try and link these ideas together. So the type of content that they would expect you to give then is shown here under the indicative content. So what you really need to be talking about is how the resistance of the light dependent resistor is going to be impacted on by the conditions based on light intensity in the room. So the higher light intensity, the lower the resistance. And so as light intensity increases, the idea is that you're going to have a lower resistance for a circuit, which means that the reading on the ammeter will increase. So we've got the ammeter mark there. The next thing is for saying what would happen to the reading on the voltmeter down to the potential difference. So you can see here that the overall resistance of the circuit would decrease because this resistance decreased here, allowing more current to flow through, as we've already said. But that means that this resistor will probably get a greater share of the potential difference because that resistance remains the same, whereas this is getting less. So the reading on the voltmeter would decrease due to the fact that this was getting a lower share of the overall resistance. So what I'd like to do now is to use the indicative content here to improve your answer, and then try and get it into the next level up based on these ones. So remember, this is how you assess, this is what you need to do in order to get these marks here, but how you do it is by using this information that's there. Once that's completed, you can give yourself a mark out of 16 for the question, and then that's the end of the paper as a whole. I hope you've enjoyed the video and you found it useful. Thank you for listening.